Welcome you all on today's lecture. So I will explain about how to solve the numericals on single stage impulse steam turbines. So in order to solve the numericals on the single stage impulse turbine, we need to go through some formulas related to that one. So in that one, the first one is a tangential force. So this tangential force is due to change in whirl velocity or tangential component of absolute velocities. So this tangential force is calculated by using the expression m by gc into Vu1 plus or minus Vu2. So here m dot represents the mass of steam flow rate and G is taken as a 1 year. So because in a steam turbines the flow of steam taking in axial direction. For that reason U1 is equals to U2 and Vu1 represents tangential velocity at inlet and Vu2 represents tangential velocity at exit. And this tangential force is obtained in newtons. The second expression used is an axial thrust. So this axial thrust is due to change in axial velocity components. And this one is calculated by using formula f of a is equals to m by gc vf1 minus vf2. So here once again m is equals to mass flow rate of steam, g is taken as a 1, vf1 is equals to flow velocity at inlet and vf2 represents flow velocity at exit. Here also the axial thrust is available in newtons. Third one is work done per kg of steam by the rotor. The work done per kg of steam by the rotor is calculated by using the expression W. The work done is also termed as E or delta H. Now work done is equals to U into Vu1 plus or minus Vu2. Once again here blade U represents the blade velocity and Vu1 and Vu2 represents tangential velocity at inlet as well as exit. And in short that is taken as U into delta Vu. So this delta Vu represents the change in tangential velocity. And unit of that work done is joules per kg. So because here m is taken as a 1 kg, or the mass flow rate is taken as a unit mass. Then blade efficiency or diagram efficiency denoted by neta B. So this is calculated by using the formula or the denoted by neta B or neta R. The blade efficiency or rotor efficiency is a ratio of work done per kg of steam by the rotor to the energy available per kg of steam at inlet. Now work done per kg of steam by the rotor is denoted by W and energy available at the inlet of the turbine. So at the inlet of the turbine the kinetic energy is available. The kinetic energy is given by V1 square by 2G. And here the 2 at the denominator taken to numerator. For that reason that expression becomes the 2 into U into Vu1 plus or minus Vu2 by V1 square. And it is termed as 2 into U into delta Vu because Vu1 plus or minus Vu2 is there. This is a change in tangential velocity is denoted by delta Vu and denominator is a V1 square. So that is the expression for blade efficiency or diagram efficiency. Next expression for stage efficiency. The stage efficiency is defined as the ratio of work done per kg of steam by the rotor to the isentropic enthalpy change per kg of steam in the nozzle. The ratio of work done per kg of the steam by the rotor to the isentropic enthalpy change per kg of the steam in the nozzle. Now refer this HS diagram, entropy diagram. So initially the steam supplies to the turbine at higher pressure. So here that is taken as a P1 pressure, and energy transfer occurs in that rotating element in a turbo machine. So finally steam is get exited at atmosphere pressure or at lower pressure. So now, this diagram shows the change in enthalpy from the inlet of the turbine to the outlet of the turbine. So here the line 1 to 2 that represents the actual enthalpy drop in a turbine. The position 1 represents the enthalpy 1, the inlet of the steam to the turbine. At that time pressure may be maintained at a 10 bar or more than 10 bar. So then that steam is flowing through the rotating element or the rotor, and its enthalpy drop occurs, and finally the steam is get exited at the lower pressure. Here the pressure is shown as a 0.5 bar, and this curve 1 to 2 line that shows actual enthalpy drop, and here dotted line, the vertical dotted line shows the isentropic enthalpy drop, that is indicated by the 1 to 2 dash. So now note down the corresponding enthalpy values for P1 pressure as well as isentropic enthalpy drop position, that is H2 dash, as well as actual enthalpy drop position, that is H2 on HS diagram. So this one is measured from the molar chart. So now the stage efficiency is a ratio of work done by the rotor to the isentropic enthalpy drop, that is given by W by delta H naught dash is equals to, the work done is given by U into delta VU by G, and isentropic enthalpy drop is denoted by delta H naught dash or 1. So now or the stage efficiency is also product of blade efficiency and nozzle efficiency. So here the blade efficiency is given by U into delta VU by GC to the ratio of V1 square by 2 GC, as well as nozzle efficiency is given by V1 square by 2G by delta H naught 1. So after substituting this expression in stage efficiency, finally we are getting the stage efficiency as U into delta VU by delta H naught dash, that is a work done by the rotor to the enthalpy drop in a nozzle. So for that reason the stage efficiency is also termed as, it is a product of blade efficiency and nozzle efficiency. Next expression for power developed. The power developed is a product of mass flow rate of steam into work done, that is M into the work done is given by U into VU1 plus or minus VU2. There is a change in tangential velocity, so that is equals to power developed is equals to P is equals to M into U into delta VU, and that is power is obtained in watts now. So these are the some important expressions used in a steam turbine topic in order to solve the numericals. Now move on to the first numerical on this single stage impulse turbine. A single stage impulse turbine has a diameter of 1.5 meter and running at 3000 rpm. The nozzle angle is 20 degree. Speed ratio is 0.45. Ratio of relative velocity at outlet to that at inlet is 0.9. The outlet angle of the blade is 3 degree less than inlet angle. Steam flow rate is 6 kg per second. Now draw the velocity diagrams and also find the following. First one is velocity of wheel, second one is axial thrust, third one is the blade angles, fourth one is power developed. So after reading this numerical, list out all the given data from this one. So now a single stage impulse turbine, that means this problem is related to single stage impulse turbine. There is only one stage present. Has a diameter of 1.5 meter, that is d is equals to 1.5 meter, and speed of the rotor is given, that is running at 3000 rpm, that means n is equals to 3000 rpm. Nozzle angle is 20 degree, that is alpha 1 is equals to 20 degree. Speed ratio is 0.45, so that is denoted by 5. That speed ratio is equals to ratio of blade velocity to absolute inlet velocity, that is u by v1, so that is equals to 0.45. Ratio of relative velocity at outlet to that at inlet is 0.9, so that is called as a blade velocity coefficient, that is denoted by C of B is equals to ratio of VR2 by VR1, so that is equals to 0.9. The outlet angle of the blade is 3 degree less than inlet angle, so that means the beta 2 angle is less than 3 degree less than the beta 1 angle. For that reason beta 2 is equals to beta 1 minus 3 degree. Steam flow rate is 6 kg per second, that is m is equals to 6 kg per second. Then after taking this given data, then draw the velocity diagram here and also find the first one is the velocity of whirl. The velocity of whirl is equals to Vu1 as well as value of Vu2. Second one is axial thrust, that is given by the F of A. Third one is blade angles, that is beta 1 and beta 2. Fourth one is power developed, that is P. By using the expression, the blade velocity is equals to pi dn by 60. So here d value is given as 1.5 meter and the speed n is given as 3000 rpm, and find out the value of u here, that is a 235.6 meter per second. Then by using speed ratio expression, that is the speed ratio is given by phi is equals to u by v1. So here we know the value of u as well as value of phi. So then find out the value of v1. So that value is 523.6 meter per second. Now after calculating these blade velocity as well as absolute velocity v1 value, now take one scale in order to draw the velocity diagram. So here scale is taken as 1 centimeter is equals to 50 meter per second. Here scale is 1:50 means 1 centimeter is equals to 50 meter per second. Now draw one horizontal line here. Then mark the distance of u on that horizontal line. So here the u value is 235.6 meter per second. The scale is given as a 1:50 meter per second. For that reason, for 235.6 meter per second, the scale is 4.72. That means 4.72 centimeter. Now take that much of distance and mark it on a horizontal line. So after that, so here alpha 1 angle is given, that is a 20 degree. To mark that alpha 1 angle with the horizontal, then draw the line for that angle and also mark the distance or the length of V1. That means here the 523.6 meter per second is given. So according to our scale, so this distance is 10.4747 centimeter. That means 10.47 centimeter. Mark that much of distance on that alpha 1 angle line. There is a 20 degree angle line. So now you are getting the one intersection point on that one. So now you are getting the after uh, measuring the distance on that alpha 1 angle. So now join the another end of the U point with that intersection point. So now you are getting the value of or the velocity of VR1. So measure the length of this VR1 line and represent in meter per second. So that is the velocity or relative velocity of the fluid at yield net. Then measure the angle of beta 1 by using the protractor. So measure that value, measure the value of that beta 1 angle. So from that intersection point, now draw one perpendicular line with the horizontal. So that represents the flow velocity at yield net, that is given by Vf1. So now inlet velocity triangle is get completed. In similar manner, you have to draw the outlet velocity diagram. So now, so here beta 1 angle is measured from the velocity diagram, and beta 2 value is 3 degree lesser than the beta 1 angle. So whatever the angle you got for the beta 1, so now 3 degree and mark the beta 2 angle less than 3 degree from that beta 1 angle. So now mark that beta 2 angle, the beta 2 angle, and the corresponding velocity is given by relative velocity at outlet, that is VR2. So here VR2 length is measured by using the relations the C of V into VR1. That means the blade velocity coefficient is given as a 0.9 here. So blade velocity coefficient is a ratio of relative velocity at outlet to the relative velocity at inlet. That means C of V is equals to VR2 by VR1. So now we got the value of VR1 from the inlet velocity triangle. We know the value of C of B, that is 0.9. So now by using that relations can find the value of VR2. The VR2 is equals to C of B into VR1. So measure that, calculate that VR2 value, take a scale for that velocity and mark it on the beta 2 angle line. So now join this intersection point of VR2 line with the one end of the U. So now we are getting the absolute velocity at yield net. We are getting the absolute velocity at yield net. So from that intersection point, draw one perpendicular line, the horizontal. So that is a VF, that is a flow velocity at outlet. So now inlet and outlet velocity triangle is get completed. So then measure the delta VU. So delta VU represents, so in this velocity triangle, the delta U represents what? The summation of VU1 plus VU2. That is a VU1 plus VU2 is equals to delta VU on this velocity diagram. And also find the alpha 2 angle. Then what about this delta VF? The delta VF that represents the difference in heights of the VF1 and VF2. So that is the difference of the axial, the flow velocity line VF1 and VF2, that is termed as delta VF. So measure these two parameters from this velocity diagram, that is a delta VU as well as a delta VF. After this, list out all the values from the velocity diagram. So that is beta 1 value, that is a 35 degree, and beta 2 is equals to 3 degree lesser than the beta 1, for that reason it is 32 degree. Then delta VU is equals to 495 meter per second. Delta VF is equals to 30 meter per second. And now the first part of the numerical is what? To calculate, the first part of the numerical is calculate the velocity of whirl. The velocity of the whirl is given by delta VU, so that is a 495 meter per second. So what about the second part here? To calculate the axial thrust. The axial thrust is calculated by the formula F of A is equals to M by GC into delta VF. Now substitute the values of M as well as the delta VF, and that answer is 180 Newton. Next, calculate power developed The power developed is given by the formula P is equals to m dot by Gc into U into delta Vu. You know all the values of this expression. Just we know the value of m as a 6 kg per second, U value is known, and delta Vu value is known. Substitute on this expression and find out the power developed. So the answer is 700 kilowatt. And third part on that numerical is to calculate what blade angles, that is a beta 1 angle as well as beta 2 angles. So this is a method of solving the numericals on single stage impulse turbine. Now one more thing, they calculated, that is stage efficiency. The stage efficiency is calculated by the expression. This is the expression 2 into U into delta Vu by V1 square. Substitute the values here and that answer is 85.1%. Next, move on to the second exercise or second problem on single stage impulse turbine. So here the steam issuing from a nozzle to a level turbine with a velocity of 1000 meter per second. The nozzle is 20 degree. The mean blade speed is 400 meter per second. The blades are symmetrical. The mass flow rate is 1000 kg per hour. Friction factor is 0.8. Nozzle efficiency is 0.95. So now calculate first one the blade angles, second one axial thrust, third one work done per kg of steam, fourth one power developed, fifth one blade efficiency, sixth one stage efficiency. So after reading this numerical, try to write all the given data from that one. So now steam issuing from a nozzle to level turbine means that level turbine is also called as single stage impulse turbine. Now with the velocity of 1000 meter per second. So here V1 is equals to 1000 meter per second. The nozzle is 20 degree. That means alpha 1 is equals to 20 degree. The mean blade speed is 400 meter per second. The value of U is equals to 400 meter per second. The blades are symmetrical. That means beta 1 is equals to beta 2. The blade angle at inlet is equals to blade angle at outlet. Mass flow rate is 1000 kg per hour. So here m is equals to 1000 kg per hour. So here the mass is given in kg per hour. So now we need to convert that into kg per second. That means to divide this 1000, the value mass flow rate is 1000 by 3600. That means 1 hour is equals to 3600 seconds, and divide that 3600 on that 1000 and get the answer in kg per second. Friction factor is equals to 0.8. That means the ratio of VR2 by VR1 is equals to C of V is equals to 0.8. The nozzle efficiency given as 0.95. Calculate first one the blade angles, that is a beta 1 angle as well as a beta 2 angle. Axial thrust F of A, work done per kg of steam, that is W, power developed P, blade efficiency neta B, and sixth one is the stage efficiency or neta S. Now take a one scale, that is 1 centimeter is equals to 100 meter per second, because here the V1 value is 1000 meter per second. So for that reason, because of a higher velocity here, we have taken a higher scale. There is 1 centimeter is equals to 100 meter per second. So now draw horizontal line and mark the value of U on that horizontal line. The U, the blade speed is given as a 400 meter per second according to our scale. So that distance is a 4 centimeter. Mark that 4 centimeter on that horizontal line. So then you know the value of alpha 1. Mark the angle alpha 1, that is equals to 20 degree by using protractor. So now draw the line for that alpha 1 angle. So in that alpha 1 angle line, mark the V1 value, the absolute velocity at inlet value, that is V1 is equals to 1000 meter per second according to the scale. So this value is equals to 10 centimeter. So now mark the 10 centimeter line on that one. Now we are getting the V1 length. Then join another point of the U with that intersection point of V1 line. So that is known as a relative velocity at inlet. Measure beta 1 angle by using protractor. Correct. Now mark the measure the angle of beta 1. Then draw one perpendicular line with the horizontal. So that represents the flow velocity at inlet. So if you know the value of beta 1 or blade angle at inlet, so that should be equals to beta 2 because the blades are symmetrical. Now mark beta 2 angle and also draw the VR2, that is relative velocity at outlet. So that is calculated by using the relation C of B into VR1. So now we are getting another end of the VR2 is joined with the U line. So now we are getting the absolute velocity at outlet and draw one perpendicular line here. So that represents the flow velocity at exit. So now velocity triangle get completed. So then measure the length of delta VU or change in tangential velocity. Here it is a tangential velocity. Change in tangential velocity is equal to VU1 plus VU2. Now also measure alpha 2 angle as well as delta VF. The difference of heights in VF1 line as well as VF2 line, that is delta VF. Then from the graph list out all the values. So that is beta 1 is equals to beta 2 is equals to 32.4 degree. Delta VU is equals to 971.2 meter per second. Delta VF is equals to 68.2 meter per second. Axial thrust is equals to, so here axial thrust is calculated by using the expression m dot by gc into delta VF. So that is equals to, that value is 19 Newton, and work done per kg of steam is calculated by using formula W is equals to U into delta VU. So that is equals to 388.5 kilojoules per kg. So now power developed is calculated by the expression m dot into W is equals to 108 kilowatt. Then find out the blade efficiency, that is calculated by using the formula 2 into U into delta VU by V1 square, and that answer is 77.7%. Also calculate stage efficiency. So stage efficiency is a product of blade efficiency and nozzle efficiency. We know the value of blade efficiency as well as nozzle efficiency values. Substitute here and find out the stage efficiency. So that is equals to 73.8%. So that is a second numerical on the single stage impulse turbine. Next, move on to the third numerical on single stage impulse turbine. Here steam flows through the nozzle with the velocity of 450 meter per second at the direction which is inclined at an angle of 16 degree to the wheel tangent. Steam comes out of the moving blades with the velocity of 100 meter per second in the direction of 110 degree with the direction of blade motion. The blades are equiangular and the steam flow rate is 10 kg per second. Find power developed, power loss due to friction, axial thrust, blade efficiency and blade coefficient. So from this given numerical, write the given data. The steam flows through the nozzle with the velocity of 450 meter per second. That means V1 is equals to 450. The direction which is inclined at an angle of 16 degree to the wheel tangent, that is alpha 1 is equals to 16 degree. Steam comes out of the moving blades with the velocity of 100 meter per second, that is V2 is equals to 100 meter per second. The direction of 110 with the direction of the blade motion, that is alpha 2 is equals to 110 degree. Blades are equiangular, that is beta 1 is equals to beta 2, and steam flow rate is given as a 10 kg per second. The m is equals to 10 kg per second. So then find out power developed P, power loss due to friction, axial thrust F of A, blade efficiency and blade coefficient, that is C of B. Take one scale. Scale is taken as 1 centimeter is equals to 50 meter per second. So now draw one horizontal line. So here the u value is unknown. The blade velocity value is unknown. So there is one more type of the numerical on this single stage impulse turbine in case the blade velocity is not given. See, now we know the value of alpha 1 at, on a horizontal line at any point. Mark that alpha 1 angle, that is 16 degree, and that velocity, the corresponding velocity, that is a v1 value is known, that is a 450 meter per second. According to that scale, that length is 9 centimeter. Mark that 9 centimeter on that line. That is a v1 value. Now we know the value of alpha 2, so that is given as 110 degree with the direction of the blade motion. So mark the angle of alpha 2 as 110 degree, and v2 value is given as 100 meter per second, that is equals to 2 centimeter according to our scale. Mark that distance on that alpha 2 angle line. Then from that intersection point, draw horizontal line, draw vertical line to that horizontal, that is VF1, and also draw VF2 line. Now measure the heights of this VF1 as well as VF2. So after measuring that, now take the same length of VF2, take the length of VF2 and draw same length in downward direction. So whatever the dotted line indicated over here, so that length is equals to the length of the VF2 above the horizontal line. Join that VF2 line with that intersection point of V1 and VF1. So now this line passing through that horizontal line. So once again the intersection point on that horizontal line is taken as another point of the U here. See. So now that is distance is measured, that is the VR1, and the corresponding angle is taken as a beta 1. So if you know the value of beta 1, the beta 1 is equals to beta 2, and draw the beta 2 angle, and that is passing through the intersection point of the VF2 and the V2 line. So these two, the beta 1 and beta 2 angles should be same according to the data given in numerical. So then measure the VR2 line and velocity, corresponding velocity. Then mark distance of U and measure the distance of U as well as measure the distance of delta VU, and also measure the delta VF, that is a change in axial velocity from the inlet to the exit. So now this velocity triangle is get completed, and later you have to calculate the required parameters or data from the given numerical. See, from the graph list out all the data values here. The U value is 167 meter per second, beta 1 is equals to beta 2, that is equals to 25 degree, delta VU is equals to 466.8 meter per second, VR1 is equals to 293 meter per second, VR2 is equals to 222 meter per second. So now power is calculated, and that value is 780 kilowatt, and power loss due to friction, that is calculated by using the formula M by Gc into delta HF. So that is equals to, here HF is equals to 1 by 2 Gc into VR1 square minus VR2 square. After substitution of these values on that expression, we will get the answer as 182.8 kilowatt. Then axial thrust F of A is equals to 301 newtons, and the blade coefficient is given by the relation C of B is equals to VR2 by VR1. Substitute the values of VR2 and VR1, and we are getting the blade coefficient as 0.758. So this is a method of solving the numericals on single stage impulse turbine. Thank you.